Welcome back to this lecture on the applications of Laplace transforms. In the previous lecture, we had seen what an inverse Laplace transform is, and I had shown you a table of Laplace transforms, and I showed you with a couple of examples on how to use this table of Laplace transforms to solve a relatively difficult problem, which otherwise is very difficult to solve, okay, using conventional techniques. So now we will apply the same procedure to solving a few physical problems, 3 physical problems specifically. So first is a simple harmonic oscillator. So you all are familiar with this problem. So I'll just have a brief recap of what this problem is all about. So let's say simple harmonic oscillator, you could take a spring like this, okay. The spring has got a spring constant K. I'm assuming that the spring is massless, and this is an unloaded spring because I'm not putting any mass, okay, I'm not loading it with any mass. So if I don't disturb the spring is going to be at a natural length. So L0 is the natural length of the spring. Okay, so L0 is a natural length, and in this case the spring force will be 0. The spring force, it's a restoring force. That restoring spring force will be 0. Okay, so this spring force will be non-zero only if the length of this spring is different from its natural length. Okay, so if the length of the spring is equal to the spring equal to L0, which is the natural length, the spring force will be 0. But if it is different from L0, either if it is greater than L0 or it is less than L0, then the spring force will not be 0. So if it is greater than L0, that means you have extended the spring, then there is going to be a spring force which will try to bring it back to its natural length. If you compress the spring, that is the length of the spring is lesser than the natural length, then the spring force would try to bring it back to its natural length again. Again, in that case, there is going to be a spring force. So now this is an unloaded case, which is not at all interesting for us because we want oscillations in a particle. So what we do is now we fix a mass to it. Okay. Now the moment we put a mass to it, the spring will no longer be in its natural length. Okay, it is going to expand. Why? Because the moment I put a mass here at this point, okay, if you draw a free body diagram here, at this point there is going to be a force due to gravity in direction, which is going to accelerate it downwards. And once it accelerates, this point accelerates downwards, the length of the spring will increase. So as a result, the spring force will also increase. Spring force, which is directly proportional to the extension and or compression in the string, that is going to go on increasing. So eventually there is going to be a time when the spring force will become equal to the mass. So that is that loaded equilibrium position. So again, K, spring constant is K. The original natural length was L0, but now the spring has expanded by a certain amount, that is delta L. Okay, so loaded equilibrium, what happens is the spring force which is generated, because now you see the mass is the length of the spring is no longer equal to its natural length, it is more than its natural length. So the spring force Fs in this case will be non-zero, and this spring force will be equal to mg because it's in the equilibrium condition. And of course the spring force is nothing but spring constant times the additional length, so K into delta L, that will be equal to mg. Now what I do is, now this is in equilibrium state. Now if let's say I take this mass and I just pull it down, okay, I pull it down and I release this, what will happen? It's going to oscillate. So during this oscillation phase, okay, at an instantaneous point, at certain point of time, again, I take a photograph of this. Now let's try to analyze this. L0 was its natural length, okay. The moment I put a load in this, then its length, natural length, from that it will increase by delta L. Okay, that will become the new equilibrium. Okay, now it is oscillating. So when during its oscillation, when it undergoes an extension, additional extension of x of t, we call that as the instantaneous position. So at the instantaneous position, what will happen is the spring force will be greater than mg. At the loaded equilibrium, the spring force will be equal to mg, but at the instantaneous position, the spring force will be greater than the weight of this particular mass. Okay, so using Newton's second law, net force is equal to m into a. Okay, I'm taking the downward direction as the positive direction, so m into a is equal to mg minus, because the spring force will be directed upwards, and the spring force is nothing but K times the extension in the spring with respect to its natural length. So with respect to its natural length, what is the extension? Delta L plus x. So K into delta L plus x. Okay, so mg and K delta L will get cancelled because in the loaded equilibrium condition we have seen mg is equal to k delta L, so these two will remain, these two will get cancelled. So as a result, this will be the equation that we need to pick up from here. So ma is equal to minus kx, whatever is the extension above or below is loaded equilibrium position. Okay, that extension multiplied with k with a minus sign, of course, that is going to be the Newton's second law, expression for Newton's second law of motion. So ma is equal to minus kx. So this is the equation for the simple harmonic oscillator. So this is the starting point. Okay, so I have a spring. Okay, to that spring is attached a massless spring. To that is attached mass m, and x naught is its equilibrium position. Okay, not equilibrium position. X naught is the position of this mass at t equal to 0. Okay, initially when I start observing this, what was the position? That position is x naught. Then it undergoes oscillation. That oscillation we refer to it as x of t. So the initial conditions, we need to keep in mind the initial conditions here. I'll assume that the initial position, the particle is at position x naught, and I will assume that the initial velocity is 0. So I will start my stop. I'm watching this particle, okay, and I'm keeping track of the time that it takes to oscillate. So I'll start my stopwatch when the particle, its velocity is 0. That means either of the extreme positions, either at the lowest extreme position or the uppermost extreme position, because that's where it turns and its velocity will be 0. So I'm keeping the initial position x of 0 to be x naught and initial velocity to be x prime, that is differentiation of x of t, x prime at 0 will be equal to 0. Okay, so these are my initial conditions. Now from Newton's second law, of course, we have seen ma is equal to minus kx. So ma is nothing but acceleration is second derivative of position, so m into x double prime of t, and this I bring it on this side, so plus k x of t. So let's call this as equation number 1. So let us say that capital X of s is the Laplace transform of small x. Small x is a function of time, capital X is a function of s, so capital X is the Laplace transform of this position function, let's say. Okay, so then in that case, this position function x of t will be the inverse Laplace transform of capital X. Okay, so now if we can find out this capital X, then we can directly find out what is this x of t. Now you see, what is the conventional way of solving this? Okay, it's a second order ordinary differential equation. So we have to use techniques for solving a second order ordinary differential equations, which could be involved. In this case, it is straightforward, but it could be really involved. Now, without using any differential equations, we can directly get this if we go to the transform space. Okay, so if we can find out this capital X, then we can easily find out small x by finding out its inverse Laplace transform from the table. So what we do is we apply the Laplace transform to this equation number 1. So we get Laplace transform the left hand side must be equal to 0. Now using the linearity property, okay, we can open up this Laplace transform. M goes outside because it's a constant. M into Laplace transform of the second derivative of x plus k into Laplace transform of x. So now here this can be simplified because we can use the Laplace transform of derivatives, right? We can use the Laplace transform of derivatives property and expand it to be like this. Okay, you can just refer to my lecture on the properties of Laplace transform to find out how I have done this. So this is a property of Laplace transforms. So this can be written, this Laplace transform of the second derivative of x can be written like this. Okay, so this is what we have here. So now we just substitute here because Laplace transform of x is capital X. So this is nothing but capital X. This is also nothing but capital X. Okay, so now we what will be these values? Okay, we can just use we realize that these are nothing but the initial conditions. Okay, x of 0. Okay, x at t equal to 0 is x naught, so that's why we got this x naught. X prime at 0, we are assuming that the initial velocity is 0, so this second term is going to become 0 here. So this is what we get here. Okay, so m square x of s minus s x naught minus 0 plus k x of s is equal to 0. So okay, we open this up, so we have m square x of s minus m s x naught plus kx of s. So I could take x of s common, so we'll get ms square plus k is equal to, this goes on this side, so we have plus ms x naught. So divide this throughout, divide this entire equation by m, so we'll get s square, so we'll get s square because m will get cancelled out, plus k by m x of s is equal to, m gets cancelled out because I have divided forward with m, so x naught into s. Okay, so now we will define this frequency. So this is where your frequency comes into the picture. We know that frequency is nothing but root over k by m. So k by m is equal to omega naught square. So substituting this here, so s square plus omega naught square into x of s is equal to x naught into s. So from here, capital X of s is equal to x naught into s divided by s square plus omega naught square. Bring this over here. So this is what we have. So we have found out x of s. So if we have found out x of s, then small x, that is the position, will be very straightforward. All you have to do is just take the inverse Laplace transform of this. The inverse Laplace transform of this, okay, L inverse of capital X of s will be this. That is, we have to take the inverse Laplace transform of this one, s divided by s square plus omega naught square. So we need to find out the inverse Laplace transform of this. And how do we find out this? We go back to our table of Laplace transforms. Okay, s divided by s square plus some constant square. Okay, and we find out that this entry satisfies s divided by s square plus some constant square. Okay, so this one's inverse Laplace transform will be cos of the same constant into t. Okay, that will be the inverse Laplace transform. So we can just use this. We can just pick this up from here and we can use it here. So this one's inverse Laplace transform is cos of whatever is that constant into t, cos of omega naught t. And this looks very familiar, right? Because it has, we are expecting it to be cosine, because our initial condition also says that we want to start at a point where it is at a zero velocity. Zero velocity means it must be at its extreme positions. So that is of the feature of the cosine function. So what we have got here is very, very it's the correct expression of the physical reality that we are talking about here. And you can notice here that we have not solved any differential equation at all. We just referred to that table and we got the answer here. Next, we'll go to a damped oscillator. So we take the same setup as before. Okay, same setup as before, but instead of making it oscillate in air, okay, we make it oscillate inside, let's say, some liquid. Okay, now this liquid will have some damping constant B. Just like this spring constant was proportional to the position, in a similar way the damping constant will be proportional to the velocity of the particle. So this just like the spring force, it resists an increase or decrease in its length. The damping constant it is always opposite to its velocity. Whichever direction it is moving, the damping constant will be always opposite in that direction. So rest x of t remains the same. Only thing is, when we do this, an additional force will come into the picture, which is the damping force. Okay, so additional damping force is f of d. Fd is equal to b into v. Like I said, the damping force is proportional to the velocity. So the equation of motion is ma is equal to spring force minus kx and damping force minus bv, because it is always opposite to the velocity. So that's why this minus sign here. So we bring this on this side, and m into a is nothing but the second derivative of x. Okay, and v is nothing but the first derivative of x. Okay, and then of course we have k x of t, which is equal to 0. Call this equation number 1. Now let capital X be the Laplace transform of the position function. That is, capital X is the Laplace transform of small x. Then small x will be the inverse Laplace transform of capital X as before. So we apply the Laplace transform to this equation number 1. So Laplace transform, this entire thing on the left hand side must be equal to 0. So we can use the linearity property again. So this will give us m into Laplace transform of second derivative of x plus b into Laplace transform of the first derivative of x plus k into the Laplace transform of x itself must be equal to 0. Now we can expand this using the same property, the Laplace transform of derivatives. We can use that property and we can expand this. So this is basically the expansion of this, and this one's expansion is this. Okay, and this of course will have a Laplace transform of x of t here. Okay, so now we can put the initial conditions here. Okay, so x of 0 is x naught, and here again we are assuming that the initial velocity is 0. So x prime of 0 also will be equal to 0. So this will vanish. Okay, so x of 0 will get a x naught here, and we'll get an x naught here, and this is going to be 0. And here we'll get a capital X, here we'll get a capital X, and here also we'll get a capital X. So 3 different places. So we have m s square capital X minus s x naught. Okay, this will be 0 plus b into s capital X minus x naught plus k into capital X. This must be equal to 0. So this is the equation that we got. So as before, we collect all the capital X terms together. So ms square plus bs plus k into capital XS minus m x naught into s minus b into x naught. These are the last two remaining terms. So from here we'll just take it on this side. So we can write this capital X of s is equal to x naught ms plus b divided by ms squared plus bs plus k. Now we divide both the numerator and denominator by m. So when you divide both the numerator and denominator by m, so we'll get s plus b by m divided by s squared plus sb by m plus k by m. Let's call this equation number 2. So now we will try to simplify this. Okay, we can simplify this. First we'll simplify the denominator. We can simplify the denominator into by completing the squares. So what we have here is s squared plus b by m into s plus k by m. Okay, so what we do is this quantity b by m into s, we just write it as, we multiply by 2 and divide by 2. So we have 2 into b by twice m, that dividing by 2, that will come here into s. Okay, then we have b by twice m whole square. You add and subtract b by twice m whole square. Basically whatever we have got here, we'll just add and subtract. So b by twice m whole square plus and minus. Okay, so it's basically the same thing. Now if you note down this one, this is nothing but s plus b by twice m whole square. Okay, so this one a plus b whole square, if you apply a square plus twice ab plus b square, so you'll get s plus b by twice m whole square. This is what we have, and whatever is remaining, we'll just put it together. So k by m minus b square by 4m square. Okay, so this is what we have. So we call this equation number 3. So this denominator can be written in terms of this. Okay, so of course we'll assume that the damping is positive. Okay, we'll assume that the damping is small. And how do you assume that the damping is small? We can assume that the damping is small by ensuring that b square is less than 4mk. Okay, so if you put b square is less than 4mk, that will ensure that this second term will be always positive. We can ensure that this second term remains positive by writing b square being less than 4mk. You can just work this out. Okay, this entire term, make it greater than 0. Okay, this k by m minus b square by 4m square, make it greater than 0. When you solve this, you'll get b square is less than 4mk. Okay, so that means this damping that we are talking about, it should be extremely small. Okay, it should be much less than, it should be less than 4mk. Square of the damping constant is less than 4mk. Then we'll define a frequency. Okay, another frequency, omega 1, because you can see here k by m. Okay, k by m is has got dimensions of frequency, right? So k by m, that means v square by 4m square, also has got dimensions of frequency. So this, that is omega naught. We had, in the simple harmonic case, we had defined omega naught. Omega naught was k by m. So this quantity will be less than omega naught. So it will also be some kind of a frequency. So we call it as omega 1. So omega 1 is equal to under root whatever we have in this second term. So we call this omega 1. So that means s square, that denominator, okay, this one can be written simply as s plus b by twice m whole square, a complete square, plus omega 1 square. You could write it like this. So x of s is this. Okay, so in equation number 2, we just substitute in the denominator. So we have this entire thing, I'll just write it as s plus b by twice m whole square plus omega 1 square. Now what we do is the numerator, again we'll break it down. Okay, b by m, we write it as b by 2m plus b by 2m, that is half b by m plus half b by m, right? That is going to give us b by m. So b by twice m plus b by twice m, and the second b by twice m that we have, you multiply and divide by omega 1. Okay, we do it like this, and we can now split this into two terms. One will be s plus b by twice m. Why we did that is because you see we already have a s plus b by twice m, so I want to just wanted to get that in the numerator here. So s plus b by twice m divided by s plus b by twice m whole square plus omega 1 square. Okay, so this part we break it up. Okay, this part of the numerator divided by the entire denominator, that is one part, and the other part will have And the other part what we'll have is I combine this, I had multiplied and divided with omega 1. That dividing by omega 1, I put it in the denominator here. So we have b by twice m omega 1 and my whole thing multiplied with omega 1. So that is going to be the second term. So we have broken this capital X into two different terms. So now finding once we have got this capital X, we can find out small x simply by taking the inverse Laplace transform. So small x will be simply x naught into inverse Laplace transform of this plus x naught into inverse Laplace transform of this. Of course, b by twice m omega 1, that's a constant, so I could just take it outside. Okay, so x naught into b divided by twice m omega 1, it's outside. What is left remaining here is omega 1, so that will take the inverse Laplace transform of this. So it's just a matter of finding out these two, the inverse Laplace transform of these two functions. So we'll again refer to the table, okay, to find out the inverse Laplace transform. We'll refer to this table, and in this table we'll use these two results, that is e to the power at cos kt and e to the power at sin kt. We'll use these two results. We'll just pick them up from the table of Laplace transforms and we'll use them here. So this is what we have got, x of t, and from the table we have inverse Laplace transform of this one is equal to e to the power at cos kt. Inverse Laplace transform of this is e to the power at cos kt. Inverse Laplace transform of this is e to the power at sin kt. Okay, so this is what we got from the table. So now what we do is we'll make a equal to, over here a is a constant. Let us say a is equal to minus b by twice m. Okay, a is equal to minus b by twice m, and k is another constant. That k, let's call it as omega 1. Okay, we replace this here, and once we make this replacement, we'll have s. A is equal to minus b by twice m, so s minus b by twice m, so that will give us plus, so s plus b by twice m, so s minus a again, s plus b by twice m whole square, plus k square, k is nothing but omega 1, so we have omega 1 square, so which is nothing but this entire thing, right, the Laplace transform of this, and this will be equal to e to the power a again we substitute here, so minus bt by twice m minus b by twice m into t, so minus bt by twice m cos k is omega 1, so cos of omega 1 t. Okay, so we have obtained the Laplace transform of this one. Okay, this one's Laplace transform is this simple expression. In a similar way, same way, a is equal to minus b by twice m and k is equal to omega 1, we can see that this k is equal to omega 1, okay, minus b by twice m, that will give us plus, so s plus b by twice m whole square plus omega 1 square. This is nothing but e to the power at sin kt, so we'll have e to the power minus bt by twice m sin omega 1 t. So we have this entire inverse Laplace transform, I could replace it with this, and this inverse Laplace transform I could just replace it with this. So using this, in equation number 4 we get x of t is equal to x naught e to the power minus bt by twice m cos omega 1. So this gives us a cos term and this gives us a sin term. So this is what we got. Okay, so now I take x naught e to the power minus bt by twice m, I take it common. So what we have in the first term, we have cos omega 1 t plus b by twice m omega 1 sin omega 1 t. Let's call this equation number 5. We'll try to simplify this even further. So what we'll do is we'll define quantity phi, okay, such that tan of that phi is equal to this quantity. Okay, we'll define a quantity phi such that the tan of that quantity is equal to whatever you are multiplying with the sine term here, sine of b by twice m omega 1. So this will give us x of t is equal to x naught e to the power minus bt by twice m cos of omega 1 plus this is nothing but tan phi sine omega 1 t. Tan is nothing but sine by cos, so sine phi by cos phi. Now add these two fractions. Okay, so we'll have in the denominator we'll have cos phi, in the numerator we'll have cos phi cos omega 1 t plus sine phi sine omega 1 t. Now this is nothing but, this is cos a cos b plus sine a sine b, that is nothing but cos a minus b or cos b minus a. So this will be equal to the cos of the difference between omega 1 t and phi. So this 1 by cos phi, I could write it as secant phi. So secant phi, so x naught e to the power minus bt by twice m, 1 by cos phi, I write it as secant phi. Cos of this entire thing, it is omega 1 t minus phi. Now secant phi is equal to under root 1 minus tan square phi, right? This is just a basic trigonometric identity. So secant phi is under root 1 minus tan square phi. So tan phi is nothing but b by 2m omega 1, right? tan phi is b by 2m omega 1. So you just take tan square, that is b square divided by 4m square omega 1 square. From now from here I take 1 by omega 1, I can take it common outside. So 1 by omega 1, that means here this is 1, that means this has to be multiplied with omega 1 square, plus of course 1 by omega 1 square is gone, so we have b square by 4m square which is left behind. Now omega 1, the way we had defined omega 1, I think it's over here, yeah, the way we had defined omega 1, so omega 1 square is k by m minus b square by 4m square. So this is something that we will now substitute. Okay, so omega 1 square we'll substitute, we'll replace it with k by m minus b square by 4m square. So these will get cancelled out, b square by 4m square, this will get cancelled out. And what is k by m? Okay, if you recall, k by m is, in the undamped case we had the frequency omega naught, right? Under root k by m is nothing but omega naught, so this will give us a omega naught, so omega naught by omega 1. So secant phi is nothing but omega naught by omega 1, so we could just put this back over here. So we have x of t, x naught, secant phi is omega naught by omega 1 e to the power minus bt by twice m cos of omega 1 t minus phi. And this how do you check whether this is correct or wrong? It should this should go to the undamped case. If you make this damping constant b to be very small, tending towards 0, it should go to undamped case. So if b tends to 0, then of course this will be tending to 1, and if b tends to 0, okay, if b tends to 0, then omega 1 will tend to omega naught, because omega 1 is k by m minus b square by 4m square. If this tends towards 0, what will be left behind is k by m, right? So that means omega 1 will tend towards omega naught, and b tends to 0, that means phi will tend towards 0, because tan phi will tend towards 0, so phi will tend towards 0. So phi tends towards 0, okay. Omega naught, omega 1 tends towards omega naught, so omega naught by omega 1, this will tend towards 1, this will be 1, this omega naught will tend towards omega naught, and phi will tend towards 0. So as a result, this is what we'll get, x of t will tend towards this case, which is basically the same as the undamped case. Now for simple harmonic oscillator and the damped oscillators, I have made a couple of simulations using Python, so I'll show it to you at the end of this lecture. Let's go to the next problem, which is an impulsive force. Okay, basically what happens here is, when you talk about an impulsive force, so suppose I have a particle, okay, a particle which is initially at t equal to 0, it is at the origin, it is initially at rest, that means its velocity is also 0. Now at t equal to t naught, I give it suddenly, I strike this, so this could be a billiards ball, okay, and using the cue you strike the billiards ball. You don't apply that strike, means you are striking it for a very small duration of time. You don't apply the cue stick on the billiards ball for an extended duration of time. It just strikes, right? So for an extremely small amount of time, a very large force basically acts on this one. So such a force is known as an impulsive force. So you strike this, and once you strike this, then what happens is the ball is going to now start moving. As per Newton's first law, it should continue to move with a constant velocity, because I'm assuming that there is no friction. This is an inertial reference frame, so there is no friction. So for at t equal to 0, it is at rest. At t equal to t naught, you apply a impulsive force. Then for t greater than t naught, that means after this time, this object is going to just continue to move with a constant velocity. Now this force that has been applied, that's an impulsive force. That force, it exists. It is 0, initially is 0, it is 0, 0, 0, and then suddenly when you strike this, you will get a very large force, and again it will suddenly become 0. So you could model this force, this impulsive force, you could model it using the Dirac delta function. That is the Dirac delta function, delta t minus t naught. You could note here, this is exactly the same as the Dirac delta function, that multiplied with some constant p, that is the impulsive force. So basically this is what is happening here. So we'll again take the initial conditions. So for simplicity, we'll take the initial position to be 0 and initial velocity to be 0, because it's at rest. So the force that is applied is p into the Dirac delta function. So from Newton's second law, ma must be equal to the total force. Ma is equal to F. Okay, a is the second derivative of x, and F is p delta t minus t naught. Bring it on this side, so mx double prime minus p delta t minus t naught. Now we take same procedure, we take the Laplace transform of this equation. So Laplace transform of mx double prime minus p delta t minus t naught. So using the linearity property, we break this up. So m goes outside. The Laplace transform of the second derivative of x minus p into the Laplace transform of the Dirac delta function. Now using the Laplace transform derivatives property, you could just expand it like this. And how did I get this? If you recall, I had given to you all an assignment in the previous lecture. I had asked you all to find out to show that the Laplace transform of the Dirac delta function is such and such. So I have just picked up the result here. So if you have done the assignment, you will know what I'm talking about here. If you take the Laplace transform of the Dirac delta function, it will give us e to the power minus s t naught. So this is what we have here. So from here, this will be 0 because I'm assuming that initially the particle is at the origin. So initial position is 0. Initial velocity, particle is initially at rest. So its initial velocity is also 0. So what remains is ms capital X is equal to p e to the power minus s t naught. So from here we get x of s is equal to, bring this on this side, ms square, we bring it on the other side. So x of s is equal to p by m e to the power minus s t naught divided by s square. Let's call this equation number 1. So once we have got this capital X, next step is finding out the small x. I want to find out how will this particle move, how will its position change, what is x as a function of t. That's what I want to find out, right? And we expect this x of t to be a straight line, right? After this time t naught, we expect it to be a straight line. Okay, but can we get this from here? So this is what we expect here. So how do you do that? We want to find out x of t. So all you have to do is just take the inverse Laplace transform of this. So x of t is equal to the inverse Laplace transform of capital X. So p by m will come outside. We'll take the inverse Laplace transform of e to the power minus s t naught divided by s square. So now let's say small f is equal to t. Then capital F, its Laplace transform will be 1 by s square. Basically, I want to find out what is this 1 by s square. So 1 by s square, inverse Laplace transform of 1 by s square is equal to simply t. Why I am doing this? Because I want to use the shifting property here. Because you see, what we have is 1 by s square, right? And that is basically a Laplace transform of something. And that is being multiplied with e to the power minus some other quantity, right? So that immediately brings to my mind the shifting property. Okay, so what it says is e to the power minus bs f of s is equal to the Laplace transform of f of t minus b into h of t minus b. Just have a look at the shifting property in the previous lecture on the properties of Laplace transforms. Okay, so this is the shifting property. So all we need to do is, let us say b equal to t naught. We substitute instead of b, we put t naught here. Then this equation, what do we get here? E to the power minus s t naught, e to the power minus s t naught, because b is equal to t naught, times what is f of s? F of s is equal to 1 by s square. This must be equal to L of f of t. What is f of t? F of t is equal to t. So what is f of t minus b? You replace t with t minus b, then this is going to give us t minus b, and h of t minus b will remain as it is. So this is what we have here. So if I take the inverse Laplace transform, okay, so this is equal to the Laplace transform of this. That means this must be equal to the inverse Laplace transform of this. So if I take the inverse Laplace transform of e to the power minus s t naught by s square, this must be equal to t minus t naught, h of t minus t naught. So this is exactly what we're trying to find out here. The inverse Laplace transform of this is equal to this. So substituting this, we have x of t is equal to p by m, replace this, t minus t naught, h of t minus t naught. So this is the position. Okay, so you can see it's a straight line because p is constant, m is constant, and h is having value 1 for t greater than t naught and value 0. So only thing is, it is linearly proportional. X is linearly proportional to t. So this is going to be a straight line. So it will involve a straight line. What will be the velocity? What do you expect the velocity to be? As per Newton's first law, you have applied the impulsive force. Now we expect the particle to continue to move in a straight line with a uniform velocity. So we expect its velocity to be constant. So that also can be seen here, because if you differentiate this x with respect to t, dx by dt, then only this will get differentiated. T minus t naught, differentiation of t minus t naught with respect to t is 1. So you will get p by m into h into t minus t naught. So that gives the velocity also should be constant for t greater than t naught. So before I end, I would like to just show you some of these simulations that I have done. First, we go to the simple harmonic oscillator. So let me go to the solution of this one. I think I should go here. Yeah, this is a simple harmonic oscillator. So this is the Python code for the simple harmonic oscillator. If you're interested, I could just give you this code. You could run it on your own. So here we have these quantities. So we need x naught and omega naught. Okay, x naught I'm taking it as 10. Okay, and omega naught you can get it from k and m. So I'll give a value of k and I give a value of m. So from here it will calculate omega naught, and then basically it will calculate this and it will plot this. So let's see this at work. So you should expect a cosine graph. Okay, so this is the instantaneous position. Okay, it's a cos graph because it starts from the maximum position. This will be the instantaneous velocity. Okay, and this is how the Laplace transform will look like. Okay, so you could try out, you could just play around with this. You could change the value of k, because if I put k, let's say if I increase k, okay, if I make it, it was 0.5, let's say I make it 1 point, if I make it 1, then you see the frequency will increase. Okay, because we expect the frequency to increase. If I make it, let's say 5, we expect the frequency to increase, and it does increase here. So that is your simple harmonic oscillator. Next we go to the damped oscillator. Okay, so this is the code for the damped oscillator. Once again, I mean, this is what it does. Let's see. Yeah, so basically I have just plotted, I have calculated this x of t, and of course the velocity also, and then plotted the I have calculated the Laplace transform, and I have plotted this. So here again, this is the damped oscillator. You can see here what is given is the initial position. Then you can see here initially it starts from 10. I have given 10. It starts from 10. Then the spring constant is given, the damping constant is given, and the mass is given. Okay, 0.1 means it's 100 grams. Okay, it calculates everything and it plots this. Now what will happen if I increase the damping constant? Right? What will happen? Then it should die down faster. Okay, so let's say from 0.2, let's make it 0. From 0.2, 0.02, let's make it 0.05. Okay, make it 0.05, and let's run this code again. You see it has died down much faster now. Increase this even more. Let's say I make it 0.1. The oscillations die down even faster. Okay, now let's say I want it to oscillate a lot before it dies down, so I could increase this k. Okay, so I could increase and make it, let's say 3.0. Let's say. Okay, alright, so now let's change this back. Now how far can I increase the damping? Can I keep on increasing the damping as much as I want? So let us say I make the damping to be, let's say 1. Okay, will this really work? What will happen if I make the damping to be 1? Okay, now damping is too large here, because I have not I have just given two conditions when the damping is less than the critical damping condition. So it gives me it calculates the critical damping. So damping should be less than 0.775. Okay, so at critical damping what happens? Is that point, that is that value of damping at which the oscillator does not cross its this mean position, does not cross. It just from its extreme position, it just comes to its mean position and just stays there. Okay, we can see that happening here. Okay, so it should be less than 0.775. So let's make it 0.774. Okay, 0.774, because it should be less than 0.775, and see what happens. You can see the critical damping here. Okay, you release this, it will come and it will go to its mean position. It will just stay here. Okay, its mean position is 0. It will stay there. Okay, so that's the critical damping. So once again, I'll pass on these codes to you, so you can just play around with this. And finally, this brings us to the last one, which is the impulse, whose code is given here. So let me run this code. Okay, so you can see what we're expecting here. Okay, this is the force. This is the impulsive force. What is T naught? T naught is 1. That means at t equal to 1, at 1 second, you strike this. Okay, there is going to be a very large impulsive force. Okay, very large impulsive force at t equal to 1, and then the force is going to become 0. Then what will happen to its position? From that position onwards, it will start moving. It should be a straight. Like I said, it should be linear, right? So it starts moving in a straight line, and because it moves with a constant, so its velocity also must be remaining the same. So its velocity also remains the same. So what will happen if I change this? Will this affect this? So instead of 1, let's say at 4, I make it 4. T naught equal to 4. Let's run this again. As expected, you see the impulsive force is applied at 4 seconds. So from 4 seconds onwards, it continues to move with a uniform velocity along a straight line. So that's essentially the impulsive force that we are talking about. So this brings me to the end of this lecture on the applications of Laplace transforms. Essentially, this covers your syllabus for this particular module. So you could refer to the discussion in Riley's and Arfkin's. And in case of any queries, please feel free to get in touch with me. And if you're interested in how I had developed this Python code, just let me know. You could send me a text, or you could just leave a comment here in case you want to know how I got the Python code, how I developed this Python code here. So maybe I could demonstrate that in another series of lectures. So with this, we come to the end of this lecture. Thank you.